Hey guys, welcome back. In this video, we're going to be covering the mean value theorem. So, without any further ado, let's just jump right into it. The mean value theorem states that if a function f is continuous, see, I'm telling you, this continuity thing showing up all over the place, on the closed interval a to b, closed intervals are pretty important, and differentiable on the open interval a comma b, then there exists a number between a and b such that the derivative of f evaluated at that point c is equal to f of b minus f of a divided by b minus a. So let's break this down. First step, we require continuity on a closed interval. Noticing a pattern, half our theorems are based on requiring continuity on a closed interval. Continuity is a very, very powerful thing that we love to have. And differentiable on the open interval a comma b. Now first, why do we actually have to distinguish that this is differentiable? Why is it not assumed? Well, that's because just because a function is continuous does not mean it's differentiable. Differentiability implies continuity, but not the other way around. So we have to specify differentiability. And it says on the open interval a comma b. Why do we only want the open interval? Well, that's because this number c that exists is between a and b. That means it's not equal to a, nor is it equal to b. So we're not evaluating the derivative at b or a. So f does not have to be differentiable on the open interval a comma b. Now I might be thinking, why not just make it the closed interval just so it's easier? Well, that's because you try and impose as little restraints on the theorem as you possibly can. So if you can have an open interval, we're going to have an open interval. Now, for the meat of it, when we're saying there exists a number c between a and b such that the derivative of f evaluated at c is equal to f of b minus f of a divided by b minus a. The reason this theorem has the name it does is because this quantity f of b minus f of a over b minus a, that is the average value that the function takes over the interval. What I mean by that, imagine you have a function on an interval, and over that interval you took all the values that it takes, add them up, and you find their average. Well, what this is saying is that average of that function, well, there exists a number c in that interval such that the derivative evaluated at that point is equal to the mean value of that function over the interval. So this might not seem really big, kind of whoopee kind of theorem with obvious ramifications. That's because this theorem is subtle. It's more of a building block. In fact, the fundamental theorem of calculus is proven using the mean value theorem. The mean value theorem is like the foundation of a house. You don't see it, you don't think about it. You yourself are probably not going to use it, but everything you do use is built on it. Now, a lot of things in calculus behave like this. The mean value theorem is part of the foundation of it. You don't see it. You don't know it's there. You don't know it's acting on anything. But it's there and allows us to do the calculus we wish to do. Now, to better get a feel of this theorem, we're going to do a couple examples working with it. So consider this function f of x equal to x squared on the interval 1 to 2. Well, the mean value theorem tells us that there exists a number c in the open interval 1 to 2 such that the derivative of f evaluated at c is equal to f of b minus f of a over b minus a. So we want to find that c. So what we want to use is that the MVT guarantees this number exists. We don't know what it is, but since x squared is continuous on AB, it's differentiable on the open interval 1 to 2, we know that the c must exist. So this is kind of like a jumping off the cliff kind of technique, but we know there's a net beneath us. We can't see it, we don't know what it is, but we know when we jump, it's going to catch us. So we know this c is there. We can assume it's there. We just got to go find it now. So let's do this. Well, first up, we need our derivative. What's the derivative of x squared? Well, that's just 2x. But we want to find this value c. We know it exists, but we don't know what it is. but we know it's a number. We know it's in this interval, so we can treat it as such. So we can actually plug it into the derivative and get f prime of c is equal to 2c. This is a specific number. We just don't know what it is. It's not like x, where it represents all the numbers on the interval. C is concrete. It's fixed. It's there. We just don't know exactly what it is. That's what we wish to solve for. And we know that this given choice of c, when plugged into the derivative, is equal to f of b minus f of a divided by b minus a. So we can go ahead and set up that equation. We know f prime of c, which is 2c, is equal to the function evaluated at 2, because that's the left endpoint, minus the function evaluated at 1, the right endpoint, divided by 2 minus 1, b minus a. And now just by punching those values and doing that calculation, we get that's equal to 2 squared minus 1 squared divided by 1, which is just equal to 3. Now remember, that doesn't mean c is equal to 3. That means f prime of c is equal to 3. So c is not 3. But when we take this number that the mean value theorem guarantees existence, and we plug it into the function, the output is 3. So now we have to solve f prime of c is equal to 3. But f prime of c, as we already stated, is 2c. So now we are left with this equation. 2c is equal to 3. Divide both sides, and we get c is equal to 3 halves. So c is equal to 3 halves is the value we are looking for. This is the value that the mean value theorem guarantees that it exists. It is a point in the interval such that when we plug it into the derivative, it is equal to the mean value. Now, quick recap of what we did. We found the derivative of our function. We plugged in this unknown c. We figured out what f prime of c must equal to. We figured out what f prime of c is. And then over here, we set them equal to each other. And then we just solve for c. Still a little fuzzy on, what on earth this is saying? Well, let's look at another example. Consider this function, f of x is equal to 4 minus x squared on the interval -1 to 0. Find all the values c satisfying f prime of c equal to f of 0 minus f of -1 divided by 0 minus -1. Well, if you recognize, on our interval, a is -1, b is 0, so f of 0 is f of b, f of -1 is f of a, 0 is b, -1 is a. So this is the exact setup of the mean value theorem. It's the exact setup. It's just already punched in the numbers for us. Now, when something says find all the values satisfying a condition, so find all these numbers, the first question that should come to your mind is, well, does it even exist? Like, does this number I want to look for exist? Well, 4 minus x squared is continuous on -1 to 0. The derivative of 4 minus x squared exists on -1 to 0. So the mean value theorem guarantees existence of this number. We don't know what it is, but we know it exists, so we can solve for it. So the first thing we want to do is evaluate that right-hand side, this f of 0 minus f of -1 divided by 0 minus -1. Let's calculate what that is. So by just plugging those values in f, we get f of 0 minus f of -1 is equal to 4 minus 3, and 0 minus -1, well, that's just equal to 1. So that fraction is just equal to 1. So we wish to find the c that makes f prime of c equal to 1. But to do that, we need f prime of c. So let's start with calculating f prime. We know f of x is equal to 4 minus x squared. So f prime of x is equal to -2x. And we know c exists. We just don't know what it is, but we can still plug it in. But we also know that f prime of c is equal to 1. So from that, we can conclude that -2c is equal to 1, and then we can solve c is equal to -1/2. So what we do is we calculate the right-hand side, calculate the left-hand side, set them equal to each other, and solve for c. That's literally the entire process of doing this. Once again, you probably won't be asked to do something like this in real life, calculate this value. The mean value theorem is foundation. It's what gives us the ability to do the stuff that we would actually do. Evaluating integrals, taking limits, finding derivatives. These things that we actually do are built on ideas and techniques such as the mean value theorem. So it's always there. It's always working. But you just don't see it. Now, the mean value theorem gives us a very important and immediate consequence. It's so important, actually, it was given its own name. We call this Rolle's theorem. Now, here's what Rolle's theorem states. Suppose f is continuous on the interval a to b and differentiable on the open interval a to b. If f of a is equal to f of b, then there exists at least one c in a comma b, such that f prime of c is equal to 0. This looks very similar to the mean value theorem, right? Well, it should, because it is the mean value theorem, just a very specific instance of the mean value theorem. The only difference is this criteria right here. F of a is equal to f of b. Why is that important? Well, think about back to the mean value theorem. It's f of b minus f of a divided by b minus a. So that numerator, it's f of b minus f of a. But what if f of b and f of a are the same thing? What is something minus itself? Well, it's just 0. 2 minus 2 is 0. 7 minus 7 is 0. 10 billion minus 10 billion. Big, but still 0. So, if f of b is equal to f of a, then that fraction in the mean value theorem is just equal to 0. So all Rolle's theorem is the mean value theorem in a very specific instance. Now you might be wondering, this seems kind of dumb. Why on earth do we care about this if we have the mean value theorem? Well, actually, because this one came first. Rolle's theorem was the one that was developed first, and the mean value theorem is the generalization of it. So the Rolle's theorem is what was used to actually prove the mean value theorem. Well, in some cases. Some people claim that the mean value theorem was proven separately to Rolle's theorem, but Rolle's theorem was just the motivation. It's highly controversial. But anyways, Rolle's theorem came first. Mean value theorem came later. MVT is just the generalization of this theorem. And what this theorem is saying is, if a function ends up where it started, then there is a number in between a and b where the derivative is equal to 0. This is one of those cases where I find pictures speak 1,000 words. So let's look at a picture right here. Suppose we have a function like this. By the way, this is the upper half of the unit ellipse. So it goes from -1 to 1, but it hooks through 0.5 right up here. So it's a function. It's continuous and differentiable on the open interval. What Rolle's theorem is telling us is that since f of a is equal to f of b, so this function over here is equal to the function over here, ends up where it started, then there exists a point where it has a horizontal tangent line somewhere in between. Now think back to the last section with the absolute maximums and absolute minimums. They occurred at places where you have a horizontal tangent line, where the function flattens out. Now, if you end up where you started, think about this in terms of real life. Suppose you're in a room and you start at the door, you walk around, and you end up back at the door. That means at some point you had to turn around. If you're in an enclosed space, or in this case, an enclosed interval, if you end up back where you started, there exists a point that you had to turn around. You had to stop and turn around. You're continuous. It's a continuous motion. Now, if it's discontinuous, this goes out the window. But since it's continuous, there's no jumps, there's no breaks, there's no discontinuities anywhere. At some point, you have to stop and turn around. Think driving your car down a road. You start at one end of the street, and you drive to one end of the street, but then you turn around and come back. You actually had to stop and turn around. You can't just drive in a straight line forever and appear where you started. You can't do that. That's not how that works. The only way that works is if you can magically teleport back to where you started, but that's a discontinuity. So this doesn't apply anyways. My point is this is how this works with the functions. You have a function that's at one point, right here. It does some stuff. It ends up back where it started. Then what Rolle's theorem is telling us is there's a point in here where the function turns around. That's it. It's saying there's a point where it turns around. Now, since it's a continuous function, it can't just magically just change direction. It has to come to a stop. The rate of change has to become 0. Then it can turn around and come back. That's where the differentiability thing comes in. That's the big punch of this theorem. That if a function ends up where it started, then there was a point in there where it turned around. That's one of the most fundamental things. That's the most important thing to get from Rolle's theorem. Now, once again, you might be thinking, well, this is kind of bonkers. Like, okay, cool. I mean, that kind of makes intuitive sense, but why do we care? First off, ask yourself this. If you're given that situation and you're told to walk around the room in an enclosed space and end up back where you started, how would you mathematically prove that at some point you stopped and turned around? Think about that for a little while. How would you actually prove that this is true? Intuitively makes complete sense. To end up where you started, you had to have turned around. But why? Why is that fundamentally true? Just one of those things that should mess with your head for a little bit. But Rolle's theorem gives us the mathematical backing in terms of functions that if it ends up where it started, it's continuous and differentiable, and at some point there's a place where the derivative is equal to 0, or where it turns around. Okay? So now let's see an example using Rolle's theorem. Let f of x equal to the square root of 1 minus x squared on the closed interval -1 to 1. Find the value c in the interval -1 to 1 such that f prime of c is equal to 0. Well, if you remember back to section 2.3, I believe, we actually proved that this function is continuous on -1 to 1. And I'm just going to go ahead and tell you, it's also differentiable on this interval. So it is differentiable on this interval. So at least the mean value theorem applies. But if you plug in -1 and 1 into this function, they're both equal to 0. So on the left endpoint, this function is equal to 0. The right endpoint, this function is equal to 0. So what Rolle's theorem tells us, there must exist a value c somewhere in there such that the derivative evaluated at that point is equal to 0. Or in other words, there exists a point in the interval where the function stopped and turned around. So we've been tasked with figuring out what value of c does the job. Well, since we're talking about derivatives, first thing we need to do, take the derivative. So we have f of x is equal to the square root of 1 minus x squared. Well, that means the derivative of f is 1/2 times 1 minus x squared to the -1/2 times -2x. That's the power rule and chain rule, respectively. And that just simplifies to -x divided by the square root of 1 minus x squared. Cool. So now we have the derivative. But now we want to find the value of c that gets this job done. Since we know it exists, we can hold it in our hand. We just don't know exactly the number it is. We can still treat it like a number. We can still plug it in and calculate f prime of c. But we know f prime of c must equal to 0 at this point. The Rolle's theorem guarantees that c does that job. So we can actually just plug c into the derivative and set it equal to 0. Or -c divided by the square root of 1 minus c squared is equal to 0. Now remember, here we don't care about non-existence. We only care where it's equal to 0. And when you're looking at a fraction, you're trying to figure out what value when you plug in it's equal to 0, you look at the numerator and you ask ourselves, when is the numerator equal to 0? And in this case, that's when c is equal to 0. So c is equal to 0 is the point in the interval where the derivative is equal to 0. That's all fine and dandy, and you might be wondering, why are we doing this? But Rolle's theorem is another one of those things, is it guarantees the existence of something. So a lot of things in advanced math require finding zeros. A lot of things in applied mathematics is finding where derivatives are equal to 0. It's incredibly important, especially in optimization, differential equations, a whole lot of advanced math that any engineer or STEM major is going to have to do at some point. Finding these points is invaluable. And before you dedicate a lot of time and resources, it's nice to know that what you're looking for is actually there. It's like looking for your keys, like buried in your closet somewhere. For those of you wondering, that's insane. That's happened to me. I left them in my pants. I threw them in the closet. It was a whole thing. It took me like 3 days to find them. It's really bad. But anyways, enough about that. So if you know what you're looking for is there, you can search much more comfortably. Because if you don't know it's there, then every time you come up blank, you don't know if you should keep looking because you don't even know if it exists. Rolle's theorem guarantees existence. So we go through a technique like this in a more complicated scenario, in a scenario where graphing doesn't work. Writing a basic equation like this doesn't work. Rolle's theorem still is there to help us, and it guarantees the existence of this number. All right? So that's pretty much it, and I believe that's everything I have for you on the mean value theorem. On the next section, I believe we're going to start graphing functions. I know that sounds like fun, but we're actually going to start graphing functions with precision. Not just plotting 15 values and drawing the line that best fits all of them. No, we're going to use calculus to analyze functions and learn how to graph them with pretty good precision. All right? That's all I have for you today, and I will see you next time where we will have more fun with math.